Hello, we are about to present the reinforcement learning final project, and we name it Simulation First Approach to Reinforcement Learning. Okay, so our group number is group 3, and we have 3 members here, as you can see. So let's get started. So, the first thing is our objectives. So first, our primary goal was ambitious, to train the 6 legs like robotic spy robot to walk and navigate using deep reinforcement learning. This is a complex task that goes beyond simple programming, aiming for the robot to learn this behavior on its own. Second, our hardware goal was to take the learned policy and successfully deploy it onto the physical spine robot. This is the holy grail of this kind of research, making it work in the real world, not just in the computer. Finally, to bridge the gap between those two goals, our methodological was to establish a complete simulation to real pipeline. This means creating a safe and efficient way to train the policy in a simulation first, before risking the hardware, which, as we see, was a major challenge.
The spy robot. This is a six-leg or hexapod robot designed for both education and research. It has 12 dynamic cell motors with 2 motors per leg, allowing complex and coordinated joint movements. It's also equipped with an IMU sensor, which detects the robot's orientation and helps with balance control. All 12 motors can be individually addressed and controlled in real time, which makes the spy robot ideal for testing various control and reinforcement learning algorithms. To begin, we assemble the robot following the kit instructions. We make sure it had a stable power supply and a proper communication link with our control PC using the U2D2 module. Once everything was connected, we confirmed the communication between the robot and the PC was reliable. This setup phase ensured the robot was physically ready and safely powered before any software or control testing. Here's a short clip demonstrating our physical setup process. After setting up the hardware, we move on to testing. We wrote simple Python scripts to check if the dynamic cell motors were functioning correctly. We also verified the IMU sensor readings to make sure it could detect orientation accurately. Finally, we tested basic commands such as stand up, which helped confirm that the robot responded correctly to our control signals. These tests showed that the robot was ready for further development and experiments. Here's a video showing our hardware test. Our main goal was to apply reinforcement learning directly to the physical spy robot. However, we quickly realized there were several major challenges. First, there's hardware risks. Reinforcement learning involves random exploration during training, which can cause unpredictable movements that might damage the motors, plastic parts, or electronic parts. Second, training inefficiency. Reinforcement learning algorithms require thousands or even millions of episodes to learn properly, but the physical robot operates in real time and need constant supervision. That makes physical training extremely slow and impractical. And finally, non-trivial results. If the robot falls or fails, it can reset itself, meaning we have to manually pick it up and reset it after every episode. Because of these reasons, doing reinforcement learning training directly on the robot wasn't feasible. The simulation problem, so we decided to move to simulation to avoid these risks. But we face another problem. The spy robot has no official simulation model. There's no prototype, which means no digital blueprint of the robot structure in Weebots, and no .wpt Word file to load it into. In short, we couldn't simulate the spy robot out of the box, which stopped us from directly applying our reinforcement learning experiments in simulation. To solve this, we look for an alternative. We chose for the Mantis Hexabot, a built-in robot model in Weebox, as our simulation problem. This model is fully functional, well supported, and already has all the necessary components for movement and physics. By using the Mantis, we could immediately start developing and testing our reinforcement learning environment and algorithms without spending time building a custom model. The mantis is almost a perfect analog for the spy robot. Both have six legs, meaning they share very similar kinematics or how the joint move. Their dynamics or how the robot behaves physically while walking are also quite similar. Most importantly, the Mantis is fully supported and documented in Weebots, making it a stable and efficient option for our experiments. So any reinforcement learning policy trained on the Mantis can later be transferred to the spy robot with only minimal adjustments.
The first part of our implementation is the algorithm. In this our algorithm, our tech stack, we have four elements. The first element is environment. We create a custom managed environment class that follows the Gymnasium Environment API standard. This is crucial for our managed robot to stabilize and train the reinforcement learning. For the algorithm, we use proximal policy optimization and PPO from the stable baseline tree library, which is great for this small environment and uh, small model for to have a great model. So the model is a multi-layer perceptron with two hidden layers or 1 to 8 nodes. It is only 1 to 8 it is kind of small, but it is enough for our model to reach a good performance. We use checkpoint callback persistent to save the model every 50,000 steps, allowing us to resume training. The second part is the observation state. Uh, the observation means what does the robot see? We feed its policy a 30 vertex state at every time step, 18 values, which are the current position of all 18 models. Each model they have six legs. Each leg has three models, so the total of 18 models and 18 values. And in the torso position, they have X, Y, Z three values, which is for the wall, and they also have three linear and three angular velocity values, so another six values. And for the orientation metric to detect folly, the F vector, they need three values, so the total of 30 value vector state we have to fit to the model, which is the observation state. Another thing we need is the action control. uh, how does the robot act? The policy offers 18 continuous values, one for each model, but these models don't have the sensor position sensor, so we have to train it with data control. The output is not a target position, but a change data to the current position. This encourages smoother motion. The curricular learning is the math change, which allows to increase as training progress from 0.03 to 0.08, letting the robot move gently at first, then more dynamically later. We also added the joint limits. Uh, we manually enforce the physical joint limits, for example, like plus or minus 45 degree or minus 30 to 90 degree, so that the joints are more realistically and don't go like a 30 360 degree or overly overrated. And also For the I implementation reward function, we have positive rewards and negative penalties. For the positive rewards, we want the robot to move forward. So moving forward should get positive rewards, for example, like plus 20 or plus 10. And for this one, we have options to move in X or global Y direction, but we decided moving forward in local frame is the best option because the dominant rewards that we project velocity onto the robot's facing direction, and, and it is better for the robot to get positive rewards and have more freedom. Also, we add the alive bonus as long as the robot didn't fall and it stay upright. It get a small reward every step, and it also get accumulated distance, which is a bonus for total distance travel. So the more it walks, the more it gets positive rewards. For the negative penalties, if it falls, we give a massive penalty, like for example, like minus 50 or minus 30 or something like that. Also, high instability. For our first few training steps, the robot was trying to jump, so we have to adjust the height instability, and we penalize for being too high or too low, so the robot maintain the stable height. And we also penalize if it move lateral drift. Lateral drift mean like moving sideways. We want the robot move forward, but if the robot move like side to side or backward, we penalize it and let it find for the right vectors. If it also we penalize if the robot bouncing like high vertical speed, if it moving like too fast from up and down, we penalize it and we give negative rewards. And if the robot didn't do anything, if it is just like staying without doing any action, we also is a passive is a passive action, so we also give negative penalties for that behavior too. So these are the results, and the graph you see here is the reward per EP length mean, which means the agent survival time. The left side you see is the time steps. Is 1,000, 2,000, 3,000, 4,000, 50, 5,000 steps, and these are the training steps like 0, 200K, 400K per training steps. So how many steps per the robot stay alive? It means it doesn't reset, it doesn't fall, something like that. For first 0 to 200K steps, the robot is exploring, so it is extremely chaotic, and for the time the robot is constantly falling, so it doesn't stay up too long. It is trying to find its balance and fall constantly. After that, for 200K to 1.7, here around here, it is landing well. There is a steady climb in survival time. It is going over 4,000, and the agent has soft balancing. It's now balanced. It doesn't fall anymore, and it is landing to stay upright. After 1.7 million plus steps, it's now converging. It's always staying in 5,000 steps. It doesn't fall at all. This is the max absolute limit, and it is a perfect reset. So in conclusion, the agent completely mastered the survivor step. And then the next graph you see here is the agent performance. So the first 0 to 200K stat is failing. This is 0, and this is negative reward. Above here positive reward. So the first few 1 million, 1 or 2 million steps, it is failing. It is nearly minus 50,000, something like that. Here it is like getting a lot of negative rewards because it is falling and over is trying to stand still. And after that, from 200K to 1.7 meter steps, it is landing. It is still getting negative penalties, but it is getting better and better. You see here, and Its dramatic linear increase is result, and you see the agent stops failing and is master the main goal, walking forward, something like that. And after 1.7 million steps, it is the reward becomes high and stable around here. See? And so in conclusion, the agent found an optimal policy and successfully learned to walk. And the next graph you see here is the training speed. So the first few 500k steps, it is inefficient, it is slow and unstable. Um, Computationally slow simulation results and from falling. After that, from 500k to 1.6 million steps, it's now a lot getting better, efficient. Agent is surviving, leading to long episodes, fast step course, and 1.7 million plus WC here is this joy FPS. This is a system issue because it is training too long and not agent problem here. So the graph you see here is the training speed graph, so it doesn't really affect the robot's performance. Thank you.
So I'm gonna show you and present about the reset topic. So in here you can see that this one is the first state. You see in our simulation the robot is wiggling and it's not stable and it's just trying to move. It's just not stable and it's not even standing up. So this is our the very first state. It was the complete like the first step and it was like not very good as you can see here. So this one is the second state. Now it's trying to get up and it's trying to walk. It's kind of a bit more stable. So I think like this is better than the first one. And this one is the third stick. Now it is like it finally stood up, and now it's like kind of like standing up on its own, and it can even like balance and stable its body, but it's not trying to walk. So this is not complete. This is just a stable one, and this is our final state. This is the result that we got the best so far. So now you can see that like the balance. Oh, sorry. You can see the balance is like it's like fully balanced and it's stable, and now you can see the legs is trying to walk like in the direction of its face. So this is the best one we got so far, and it's learning to walk and it's not falling down, or it's like it's just balanced and stable. So I think we this is the best one. Okay, so we have a like very successful policy in simulation. The next logical step is how do we bridge the reality gap and get this into the physical robot. This like outlines our like 4-step plan. First is policy refinement. This means we will test our policy in a more accurate digital twin of the spy robot and fine-tuning the parameters to perfectly match the real hardware models and sensors. Second, we use domain randomization. This is a powerful technique where we would train the agent in like thousands or slightly different simulations, varying things like gravity, friction, and motor power, just like in the real world. They force the agent to learn a more general and robust policy that it isn't like overfitted to one perfect simulation. In real world, like not every time or not every way is perfect for the robot to walk or even to test it out. So we need to have a more generalized. So it's not overfitted in just one perfect simulation. The third, the most exciting step, the physical transfer. This this will be a limited, extremely careful test on the actual spine robot in reality. So we start like simple, maybe just stand and balance, not just trying to walk. So the first step is the just stand and balance before ever attempting a full walk. And finally, fine tuning. Using the data we get from those like first physical tests, we will feed it back into the policy. This allows the agent to adapt to those less few percentage points or difference between simulation and real world. Okay, so to conclude our presentation, I want to summarize our key achievements. Most importantly, we successfully developed a high fidelity simulation environment for a hexapod robot. And we did this despite the complete lack of official support or models for the spine robot that we got. We built this from the ground up. This work isn't just a thought experience. This provides two tangible assets: a validated environment that can be used for future research, and successfully trained policy that has learned a stable working grade that I have shown you in the video, the finest step. So together, like this works out as the critical baseline for any future simulation to real transfer. We have built the strong foundation that makes the goal we discuss in future work not just possible, but achievable in the future. Thank you so much. And also, we have attached our GitHub link where we include our like the codes and reinforcement learning algorithm codes that we included in the project. Thank you so much.